you have to talk in the microphone because we are going to film today. So.
Das ist ja umso peinlicher, weil ich ja den Vortrag noch nicht gehalten habe.
Is it okay for you to film the last week?
Yeah, it's okay.
I think it's a nice record for that. Good morning, everyone. So, we are going to, before we start the talk this morning, I have the usual announcements for the day. So the first announcement is we are going to have a group picture. Today, apparently, our weather forecast, or the devils, are going to tell us that the weather should be okay. So we should have a picture, everybody, at 11:30 or after the marketing call, whichever is later. We are going to gather and have a picture. After the picture, the foreigner visitors and the students are going to have a time for pizza and for them to talk. We are foreigner visitors, for me it's a very clear definition, but if there are questions, I think that I may list the names. And we are going to have tonight samba, and this is our organizer for samba with the help of Francisca. The place is called Dandy Brasil, and it's in Ipanema. I still don't have the address, but basically we figured that out. Joan Angelica. Okay, it's very precise address, as you can see here, Joan Angelica, but you should have no problem finding it. In any case, she's handling everything on that side. Rua Joan Angelica. Okay, so without further delay, again.
We meet at 7:15 at Leblon Flat. Register sometime in Leblon if anybody wants to come along, and then we walk there, so it's very close. Otherwise, we have to find out the meet.
Yes. Okay. So as you see, it's Brazilian style, very relaxed, no stress. We are going to have now Professor Marcelo Magnasco from the University of São Paulo, Universidade Estadual de São Paulo.
Good morning, everybody. So I have the pleasure to announce Professor Martin Nowak, now at Harvard University, who will give us a talk this morning on evolutionary graph theory.
Thanks a lot. So today, I will give a talk which I have never given before, and that's unusual, so that normally you recite your old stuff, but today everything is new, and 3/4 of it is unpublished, and all of the slides I have written, but I have actually seen never before, and also most of the things I have really thought very carefully, so everything is very new here. And before I begin, I would like to write down again this equation I need to write down, which essentially contains 1/2, if not more, of all of mathematical biology. And this was the equation which was invented by Joseph Hofbauer, Carl Sigmund, and Peter Taylor. And it's also what the famous book is about. And this is the replicator equation. And in the replicator equation, you have so you have the n the interior of the simplex is invariant and all the faces are invariant. For the linear equation, a complete classification is possible for the simplex S3, but not for the simplex S4. On the simplex S3, you can have heteroclinic cycles, as Carl discussed, which have a kind of irregular behavior because you start somewhere, you go closer to the boundary until one of the species goes out and then another one reaches fixation, and you cannot really predict which one. And on the simplex S4, there can be limit cycles and chaos. And this equation now describes selection, wherever selection depends on what others are doing in the population. But it describes selection for an infinitely large population. It's a deterministic description for an infinitely large population. So essentially somewhere here is the assumption that the population size is infinity. And we have a deterministic description of population dynamics. And my talk today will be about finite n. Everything I will mention in my talk today is a finite population size. And this necessarily introduces or asks for a stochastic approach. And in the first part of my talk, I will deal with cases of finite population size where the fitness is constant. And in the second part of my talk, I will deal with a situation where the population size is finite and the fitness is frequency dependent in the usual linear way that describes evolutionary games. And mathematically, there are very interesting open problems. So for example, you can write down, this is not the only equation to describe frequency dependent fitness. There would be others to describe the dynamics of games. Similarly, for a stochastic process, there would be many different stochastic processes to describe the situation. And an interesting question is which stochastic process converges to which differential equation in the limit of large population size. And often this is actually very difficult to understand and difficult to prove. So I can now go into my talk, which I have entitled Evolutionary Graph Theory, because it's the... now I can turn it off, right? Because somehow it's the most fun thing, and the name was invented by my student, Ares Lieberman. But in fact, my talk is in 4 parts. First, I will review with you the Mirena process, which is a standard way to describe that stochastic selection in population genetics. It was invented by Pat Mirena approximately in the 60s. Then I will describe the linear process, which makes a connection to Franziska's talk yesterday, and is a collaboration with Franziska Micha and Joey Vasa. Then I will talk about evolutionary graph theory, and this is a collaboration with Ares Lieberman, Michael Brenner, who's an applied mathematician at Harvard, and Christoph Howard, who has arrived today. And then finally, I will talk about evolutionary game theory in finite populations, and this is a collaboration with Christine Taylor, who is a pure mathematician, who is a student of Yao's, who has now turned to mathematical biology, Akira Sasaki, a well-known mathematical biologist, and Drew Fudenberg, who is a leading game theorist in the economics department at Harvard. So this is the Mirena process. Imagine a box of balls or something like of types, like an urn, and the population size is n. And now you define the stochastic process in elementary steps. In one elementary step, you choose one individual, and you do this proportional to fitness. So if the red guys have a higher fitness than the blue ones, then somehow more likely it will be a red one. You can sort of write down the fitness times the abundance divided by the fitness times the abundance of the other one, plus the fitness and the abundance of the red one, the red and the blue. So you choose one proportional to fitness. You produce an offspring. And you can produce an offspring with or without mutation. Then you eliminate another one, and you add this new one in its place. This is the Mirena process. The total population size is absolutely constant. And this process now describes selection and mutation in a finite population size, yes? Yes, you eliminate randomly. So you can have, I eliminate randomly proportional to some death rate, but this cancels out. So you can say all the selective difference is in reproduction. I don't care about selective difference in death. You can do both, but it cancels out. So you can do it, it's enough to do it in one, either in reproduction or in death. Yes, you eliminate this uniform probability. What I wanted to say is you can have the situation where they differ not only in reproductive rate but also in death rate, but this doesn't change the picture for the Mirena process. Now, it's a bit artificial, right? We keep the total population size absolutely constant. But this means we have a stochastic process in one dimension. And this means we can solve it. Stochastic process in 2 dimensions, it is very hard. So the Mirena process, moreover, is a birth-death process. It's not a general Markov process, because in the transition matrix, there are positive entries only in the diagonal and in the 2 off diagonal. So it's tri-diagonal transition matrix. So you can go from I equals 1 to I equals 2 to I equals 3, and Pij is now the probability to go from I to j. The matrix P is the transition matrix for the Markov process, and it's tri-diagonal here. It's an n times n matrix, where n is the population size, and it's a birth-death process because you can only make one step in each direction. The Mirena process has 2 absorbing states. So if you wait long enough, it will be either all red or all blue in the absence of mutation. So we study now the Mirena process without mutation. No matter where you start, you will definitely end up in all red or all blue. And now we can describe the probability xi to reach state n when starting from state I. So when you start from state I, with probability xi, you go to all blue. With probability 1 minus xi, you go to all red. These are the only 2 options. And now we can calculate this probability because it is given by this recursion. What is the probability to go to all blue starting from state I? It is simply the probability to go from I to I minus 1, and then the probability to go to all blue from there. Or the probability to go from I to I, and the probability to be absorbed from there, or the probability to go from I to I plus 1, times the probability to be absorbed from I plus 1. So it's given by this recursion. And this recursion can be solved. And we are very interested in the following question, and this is x1. This is the probability to reach state n when starting from state I equals 1. So you want to know, you introduce one new mutant here. You want to know, does this mutant reach fixation? This is the fixation probability of a new mutant. Fixation means the mutant takes over the whole population. And this is the probability x1, and that's what we want to calculate. And 1 minus x1 is the probability that the mutant dies again. This was an unsuccessful invasion attempt as opposed to a successful invasion attempt. Now suppose the new mutant has relative fitness R. 1 is the fitness of the resident population of the red guys. And R is the fitness of the new mutant. If R is greater than 1, the mutant is advantageous. If R is less than 1, the mutant is deleterious. And if R is equal to 1, the mutant is neutral. And now the fixation probability that can be calculated by solving the recursion is given by this expression here, x1, which we call rho. I will call this rho later, it will come again and again. Is 1 minus 1 over r divided by 1 minus 1 over r to the power n. And for a neutral mutant, r equals 1, this expression converges to 1 over n. This is Kimura's famous result. The probability of fixation of a neutral mutant is 1 over n. And it's very intuitive because if it's totally neutral, if you wait long enough, one of these guys will be the ancestor to all of them. And it's that one with probability 1 over n. It's completely intuitive. Now, we observe for an advantageous mutant with r greater than 1, the fixation probability is greater than 1 over n. So we will use this later as a measurement for whether or not something is advantageous or deleterious. In a frequency-dependent situation, where the situation will be more complicated, we will define if you have a fixation probability greater than 1 over n, you are advantageous mutant. Otherwise, you're deleterious mutant. Now, yesterday, Franziska discussed that cancer is an evolution that nobody wants. So this is an evolutionary process where the organism would prefer it wouldn't happen. So my question then is, and this goes to the second part of my talk, to the linear process, how can we design a population of reproducing cells without evolution, where we suppress selection, for example. And this is the linear model. And this is a collaboration with Francisco Mico and Joey Baza. So as opposed to the Mirena process, we imagine the players now lined up on a one-dimensional table. This is a table where this has a kind of wall and this has an edge. In each elementary step of the stochastic process, you select one individual for reproduction, again proportional to fitness. Proportional to fitness. You divide it, you put one offspring in its place and the other offspring to the right of it. So in the Mirena process, somehow sloppy, we said you take one cell and you put its offspring back. Here you have to be more careful. You have to take into account the biological fact that, say, a cell divides to give rise to two offsprings. It's replaced by two offsprings. Because otherwise you introduce asymmetries which will change the picture. So also with probability 1/2, that one is mutated. With probability 1/2, that one is mutated if you want to study the mutation dynamics. While you do this, you shift the others to the right here. And then the last one falls off the edge. This is a very visual, very intuitive process. And interestingly, it captures exactly the way how tissues are built in a multicellular organism. As Francisco described the colon crypt yesterday, or many other tissues, the same principle. There is a slowly dividing stem cell that continuously renews the tissue. There's a cell here which divides, and all these are its offspring. And that one, the last one, undergoes apoptosis, dies. This is the way how tissues are organized. And we can now ask, what's the consequence of such an organization? Precisely, we can say, what is the fixation probability of a neutral mutant? So the fixation probability of a neutral mutant is 1/n. Very easy. If the mutant occurs here, it will be fixed. If the mutant occurs anywhere else, it won't be fixed. So a neutral mutant appearing anywhere in that population will be fixed with a probability of 1/n, as before. So the linear process changes nothing with respect to neutral evolution. But what's the fixation probability of an advantageous mutant? It's also 1/n. Has to occur here. Because no matter how advantageous it is, it will be washed out once they come back when they divide from here. So this is somehow a process that completely cancels out selection. And we said that cancer is an evolution that you don't want. So it's an ideal defense against mutations in tumor suppressor genes and oncogenes. The perfect design to protect against mutations in tumor suppressor genes and oncogenes because they are reduced to accumulate as slow as neutral mutants would accumulate in that process. And there's a further aspect how you decelerate the evolution to cancer in this process, and this is the following. You can say the stem cell divides, say, only once per week. The tissue needs cell division because these cells have to be renewed and cells die, so tissue needs some amount of cell division. So you assume that these cells divide, for example, once per day, but that cell divides only once per week. But this here is the important time scale. So the time to cancer here reduces 7-fold with this subdivision. You replenish a tissue compartment with slowly dividing stem cells. So the rate of evolution from all red to all blue in the Mirena process is this here. This is the population size times the mutation rate times the probability of fixation, time divided by the average time of cell cycle of all of these cells here. And here you have that n times rho cancels out, it's 1, so you have just the mutation rate, you have the time, you have a factor 2, because you can either the right or the left daughter cell can be mutated. This is the important thing, therefore it's a factor 2, so it's slower by a factor 2, and in addition to this, it is slower by tau 0 if this is a much longer cell division time. And in addition to this, of course, it's much slower because of the n times rho in here. The n times rho is much greater than 1 for an advantageous mutant, like an oncogene or a tumor suppressor gene. Please ask questions whenever you like. Yes? That's right. So if a stem cell divides asymmetrically, where one daughter is the differentiated cell and one daughter is the stem cell, this is what stem cells do. And if the stem cell knows which is the old strand of DNA, it can have a much lower mutation rate than normal by always keeping the old strand. And this is an interesting suggestion which hasn't been proven, but it would greatly reduce this. So instead of a factor 2, we would have something much greater. Yes? Yes, yes. Yes, stem cells and differentiated cells. Yes, that's right. Yes, yes. So this is that like a compartment, as Francisca showed yesterday, of epithelial tissue is organized in a way that there's one or very few stem cells that are there to replenish this compartment. So now we want to generalize this process. We have now talked about the Mirena process on one hand, the linear process on the other hand, and now we wonder what is in between, or what is more general than this. So we now want to talk about a population of cells, of people, also in terms of genetic evolution and cultural evolution, where people are in individual positions and they can put their offsprings into other positions with some probability. And as I said, this is work with Iris Lieberman and Christoph Howard and Michael Brenner. So the evolutionary graph theory works the following way. Give me a graph. On each vertex there's an individual, and each edge counts how likely it is that that individual puts the offspring into that position. So you choose an individual, a vertex, for reproduction proportional to fitness, and then you choose where to put its offspring according to the weights of the edges. This is a generalization of both the Mirena process and the linear process. Actually, it's a generalization of the Mirena process, but the linear process is more complicated because it has this shift operation. But you can envisage a linear process where the cells don't get shifted but just being replaced. And this is what is captured with this framework. For the linear process with the shift, you need a more complicated framework, and Iris Lieberman is working on that. So that's clear, that's the basic setting. The Mirena process would be a totally connected graph. Totally connected graph with equal weights. And the particular linear process would be a linear graph where all that can go into this direction. So we label the individuals, I goes from 1 to n, and the probability that offspring of I goes into position j is Wij. So we have a matrix W, and this is a stochastic n times n matrix. Because each person has to fit the offspring somewhere. Stochastic or maybe zero entry also if the individual is sort of a terminal node and can't put its offspring anywhere, but put it out. So what is the probability rho that a new mutant with relative fitness R starting in a random position takes over the population on a general graph? Here's an example. This is example 1, which is kind of a polygon. And for this polygon, it's very easy to prove that the fixation probability is the same as in the Mirena process. You can easily calculate this process, and you find out that here you get the same as the Mirena process. And this example led Michael Brenner to the conjecture which I call Brenner conjecture. And this is that if the matrix is symmetric, if Wij is Wji, then the fixation probability is the same as the Mirena process. This would mean any spatial model has the same fixation probability as the Mirena process. Space does not matter. Spatial configurations of this kind do not matter. And this conjecture was proven by Iris. Our next conjecture was, let us consider an advantageous mutant. For any graph, we have a fixation probability which is greater than what would be the linear process and less than in the Mirena process. So we thought the Mirena process is the fastest evolution you get, the linear process is the slowest evolution you get. So we wanted to prove this conjecture, but it is wrong. And Iris Lieberman found a counterexample, a very elegant counterexample, which I call the Lieberman star. And this star works in the following way. Here's a graph and you have a node here, and you have the periphery here, and in the periphery you can only put your offspring in the center, but from the center you can only put your offspring into the periphery. And the fixation probability for this can be shown first in computer simulations by Christoph Howard, and then also analytically by Erich Lieberman. The fixation probability of this is 1 minus 1 over r squared, 1 minus 1 over r to the n for large n. So essentially it means that the advantage r, probability, the relative fitness advantage of the mutant r goes to r squared. So this is an amplifier. You amplify selection, yes? No, for small n it's in between. It's in between 1 minus 1 over r and that formula. So you get the r squared. The full acceleration you get in the limit of large n. N goes to infinity.
So it's asymptotic.
Yes, asymptotic. Asymptotic is n goes to infinity. I have indicated something here that I will come back later. That's the temperature. Eres introduced the notion of a temperature of a node. The temperature is the sum of all the weights that go into that node. The center here is hot, and the periphery is cold. In the examples that I showed before, all the nodes have the same temperature. This will lead us to a theorem. This is the isothermal theorem. So let us define the temperature of a vertex is the sum of all the weights that lead into that vertex. The temperature of vertex J is the sum over all I, Wij. And then the theorem by Lieberman, if all vertices have the same temperature, then the fixation probability is equivalent to the Mirena process. This is an amazing generalization of what Michael Brenner showed. So the W matrix has to be double stochastic, but it doesn't have to be symmetric. So we can now construct many examples where you get the same fixation probability as the Mirena process, but you don't have a symmetric matrix anymore. I should say that Eres is also generalizing the whole scheme by saying, let us introduce arbitrary numbers as the weights on the vertices. You don't choose an individual for reproduction, but you choose a vertex. You choose a vertex, and then this vertex means that individual puts it to that individual. This is a generalization of that framework. And there, I think he has you choose an edge. You choose an edge. And there he has to he has the proof, I think, for a theorem that the graph has to be a circulation. That is the same as the Mirena process. It's very elegant, but that's not yet in my talk. So then we ask, can you actually get even higher fixation probabilities? And then he invented the Lieberman superstar. And this here has the fixation probability. So this is a following structure. You have something in the center here, and the center feeds out into these leaves. The leaves feed into that node, and that node back into the center. The number of leaves and how many are in here, that should be approximately the same and should become large. So this is L equals 5 and M equals 5. And K equals 3 counts sort of the cycle, the fundamental cycle here. This is 1, 2, 3, 1, 2, 3. And as L and M go to infinity here, the fixation probability goes to 1 minus 1 over R to the K, 1 minus 1 over R to K to the N. And now if K goes to infinity, you guarantee fixation. So this is an amazing graph because it guarantees the fixation of any advantageous mutant. So you could ask, how do you have to organize a biological structures and social structures to make sure that advantageous mutants, however small their advantages, they will definitely be fixed. That's, for example, that's an example. You can get that, it's possible. It's possible to get fixation probability 1. And by the way, so this is not isothermal. Essentially, it has to be not, because otherwise it would be the same as Mirena. So this here is hot, and that is the same temperature, and they are cold. And here he invented another structure, and this is the funnel. And for the funnel here, you have one node here, which is hot, and there's a layer here that feeds into it, and every one of that layer feeds into it, and every one of that layer feeds into that one here, and that node feeds out again to all these layers. And so again, if this structure becomes large, and this goes approximately m squared and so on, then you guarantee fixation of any advantageous mutant. So before I go into my last part of the talk, I must admit that it's not quite clear to me what we are doing here and why are we doing that and why biological populations could be organized like this. But if we go back to the Lieberman star, the simple structure, simple amplifier, this is a very natural scheme of how a multicellular organism can work, and maybe the hematopoietic system does work. So that the stem cell can only give rise to differentiated cell. Differentiated cells cannot give rise to each other, but can give rise to further differentiated cells, or back to a stem cell. So to encode something like these graphs here, if you take into account cellular differentiation, is by no means artificial. We can then ask the more general question how social structures are organized to make sure that advantageous mutants sort of prevail. It's interesting, of course, that these amplifiers have a price. They guarantee fixation, but the time is becoming larger and larger. If you want to have something that guarantees fixation probability 1, the time to infinity. The absorption time goes to infinity. So there's another twist if something, how to design a structure such that the fixation of a new mutant takes very long. It's another twist. And another problem that I have posed to him is, what is the error threshold on such graphs? Can I construct graphs such that arbitrary high mutation rates are allowed? Or is there necessarily an error threshold like there is in a normal non-spatial model or spatial Mirena process? These are all open questions. So all of what I have talked about so far was constant selection. And now I would like to go to frequency-dependent selection. I want to study evolutionary games in finite population. So we consider a game between two strategies A and B, and there's the payoff matrix, and the payoff matrix A, B, C, B. So if A plays with A, then the player gets payoff A. If A plays with B, the player A gets B. If B plays with A, the player B gets C, and this is what B gets from B. A, B, C, B. It's a general 2x2 game. And now, instead of studying the infinite population, we study finite population. To consider finite population of size n, there are I players of type A and n minus I players of type B. And the fitness of A is now given by this expression, where this is, you get payoff A if you play with another A player. And you are yourself an A player, therefore there are I minus 1 other A players in that population. And there are n minus I B players in this population, and you get payoff B. The same down here. And then I introduce a parameter W, which interestingly cancels out for the replicator dynamics. If I would do this for the replicator dynamics, this parameter W would cancel out. But here it doesn't cancel out, but plays an important role. And it's the intensity of selection. And if W is 0, then there's no selection. It's just neutral drift. If W is 1, it's totally determined by the game. So W is also the fraction, the contribution of the game to fitness. So this is to say, an individual has not only this game, but has also a background fitness. It has a background fitness, and then it interacts with others. A background fitness, and then it has this interaction, and so part of the fitness comes from the interaction, and part is sort of the normal background fitness. This is the parameter W. And introducing this parameter W actually helped us to solve the question analytically, which we couldn't otherwise. So this is the fitness of A and the fitness of B, and once more I want to point out these differences. I have I minus 1 other A players if I'm an A player, but I have I A players if I'm a B player. This introduces an asymmetry which of course is not there in infinitely large populations. Now we ask, what's the fixation probability of strategy A? The same question as before, the same recursion, we solve the same recursion, we get this answer here. The fixation probability rho, so to go from 1A to all A, is given by 1 divided by 1 plus the sum over all, then the product of all, I goes from 1 to k, gi over fi, so that's the fitness of B if there are IA players, and the fitness of A if there are IA players. The product of this is sum over this. This is standard, and for example, you can also find this in the book by Cunlin and Taylor, how to solve this equation.
Excuse me, Mark,
Yes.
just mention. This reminds me of this idea of summing over all possible paths that finally people have thought about the quantum mechanics.
Mhm.
And I think there is an interpretation that's
Yeah, that should be it. Yeah. Now, And now I introduce this definition, which is interestingly, that was surprising for economists. Right? Economists don't have that. They don't have the concept of a neutral Newton. And therefore, now to introduce this definition, that was new for Gutenberg. So if the probability, if rho is greater than 1 over n, then I say selection favors A replacing B. Because it would be 1 over n, it's a neutral Newton. If it's less than 1 over n, the selection opposes A replacing B. So I have now a baseline. Because we know the fixation probability of a neutral Newton is 1 over n. And now I study a very famous example, the prisoner's dilemma. And in the prisoner's dilemma, you have you can either cooperate or you can defect. And this is one example of writing down a payoff matrix for the prisoner's dilemma. If a cooperator meets another cooperator, you get payoff 3. If a defector meets another cooperator, the defector gets 5. A cooperator from a defector gets 0, a defector from a defector gets 1. But this is the dilemma, how it can be put to people, and you can ask people like the audience here, would you cooperate or would you defect? So who wants to cooperate with the prisoner's dilemma? 1, 2, 3, 4. Who wants to defect? So most people don't play at all, but you have to make a choice. So do you want to cooperate or to defect? Who wants to defect? Just a few. Who wants to cooperate? So you have to analyze the game in the following way. If you assume that I will cooperate, you get 3 points if you cooperate, but you get 5 points if you defect. So if your assumption is that I will cooperate, you should choose to defect. If you think I will defect, you get 0 points if you cooperate, and you get 1 point if you defect. So if your assumption is that I will defect, you should defect. So no matter what your assumption is about what I will be doing, you should defect. And I argue in the same way, and we both end up with defection. This was a very rational analysis of the game, which led both of us to defect. But if somehow irrationally, we would have been much better off if we both would have cooperated. This is precisely the dilemma. So in the standard game dynamics, in order to explain it, you rely on the notion of rationality. You pose that people behave in a rational way to analyze this game, and then you end up with defection. And for game dynamics, for evolutionary game dynamics, you don't need this. For evolutionary game dynamics, you just say, let's take this matrix, let's plug it into that equation here, the replicator equation, and let's study the dynamics of a simplex S2, and you will see that the only stable equilibrium is defection. So we say that here D dominates C. You don't need to evoke rationality to explain why it is better to defect. A mixed population of cooperators and defectors always goes to defection. This is the dilemma. And now people ask, but how can you get cooperation? And one way to get cooperation is to repeat this game. And in the repeated prisoner's dilemma, you play not only one round, but you play several rounds. And now the interesting question is, what is a good strategy for the repeated prisoner's dilemma? And nobody knew that. And then a political scientist at Ann Arbor, Michigan, Robert Axelrod, had a great idea, politically a very smart idea. Instead of solving the problem, he invited his friends and the community to submit strategies. And he said, let us have a world championship of strategies playing the repeated prisoner's dilemma. Everybody plays everybody else. I will count up the number of points, and whichever strategy wins, has the most points, is the winner, is the champion. So he received 14 entries, and surprisingly, after everything was done, the simplest of all strategies won. And this was Tit for Tat. And Tit for Tat was a computer program of only 5 lines. It starts with a cooperation, and then it does whatever the opponent did in the previous line. So if you cooperate, I will cooperate. If you defect, I will defect. And it was submitted by famous game theoretician Anatol Rapoport. And then he published these results, and many people read it, and he said, okay, let's have a second world championship. And for the second world championship, he received 63 entries. Many people submitted entries, including John Maynard Smith. John Maynard Smith submitted a strategy. Only one person, Rapoport, had the idea to submit Tit for Tat again for the second world championship, and Tit for Tat won again. And this is very surprising because many people analyzed the tournament very carefully and submitted strategies that would have won the first tournament. But in the new field, they didn't win it, but again Tit for Tat won. So this led to the question whether Tit for Tat was somehow the undisputed world champion in this game. or whether there are better strategies, and this is where Carl and I also began to work in that field. And I don't want to go into this detail, I just want to say that tit for tat is a strategy which is very able to initiate cooperation in the sense that it has a bistable equilibrium with all t. So if I plug this matrix here now, which is an example for tit for tat at all t, into the replicator dynamics, I get this phase diagram on the simplex S2. There's an unstable equilibrium here, and there are two stable equilibriums at the boundaries, so either all t or tit for tat. And if you start here, you go to all t. If you start here, you go to tit for tat. And among all strategies, tit for tat is the strategy that has the minimum invasion barrier, you would say. So you have to overcome this invasion barrier. You have to introduce initially enough, a fraction of tit for tat players that is large enough to be greater than this, and then you go to tit for tat. So tit for tat and all t are bistable. And now this begs an interesting question, and the question that has been around for a very long time is the question of emergence of cooperation. People now agree that tit for tat can maintain cooperation once it is established, but how can cooperation emerge? Because if everybody plays all t, a finite amount of tit for tat players in this infinitely large population of the replicator dynamics will be wiped out. So it's unclear how tit for tat can actually start if everybody plays all t. And some people have used this as an argument to say this explains why cooperation is so rare. Because ultimately, if everybody defects, cooperation has no chance. And then some mechanisms are constructed to get over that. So for example, you could say invasion happens if tit for tat players form clusters. They form clusters and they're more likely to interact with themselves. This can also be done in a spatial model. You need specific mechanisms to explain how tit for tat can come about. But now we revisit the question in a finite population. And we will find out that in a finite population, no specific mechanism is required. In a finite population, if you play tit for tat and all t, and this is the population size n times the fixation probability rho, so if it would be 1, it's neutral. If it's below 1, it's selected, it's opposed by selection, and here it's favored by selection. It has this general form. This means there's a minimum population size and a maximum population size, which is compatible with selection favoring the replacement of almost defect by tit for tat. Without any assumption, starting with a single tit for tat player, selection pushes the tit for tat player all the way to completion if the population size is between these boundaries. And so this here plots just this, what the equation I showed before, 1 over 1 plus the sum over all the product over all. But what we want to know is what's the minimum population size, what's the maximum population size, and what's the optimum? Or for which payoff matrix is it actually possible that this curve here goes above 1? Because for some payoff matrices it will stay below 1. So we want to get analytical insights into this process. And we cannot because it's an nth order polynomial and it's impossible to solve for minimum n or for optimum n or for something like this. But the interesting twist now was to study it in the limit of weak selection. So we have this parameter w, we're fortunate to have this parameter w, we make a Taylor expansion for small w, and then we have n rho can be written in this form, where alpha is this coefficient and beta is this coefficient. This is where the payoff matrix enters, and here's the w. And you see immediately that n rho is greater than 1 if and only if alpha n is greater than beta. And alpha n greater than beta leads to this condition here. And that's a linear condition in the population size n intercity. Now, we can say that n rho is greater than 1 if and only if this linear condition holds. We can now study this linear condition for small n. The smallest possible n is 2. It takes 2 to play a game. And for n equals 2, we obtain b has to be greater than c. So I should write down the payoff matrix. Maybe here you remember the payoff matrix A, B, A, B, A, B, C, D. If we want to analyze the classical replicator dynamics for games, you only ever compare the entries in each column. You compare A with C and you compare B with D. That's the only comparison you need to have a complete classification of that equation. But for the finite population, as for n equals 2, so that it's only that an A player plays a B player plays an A player, the only valid comparison is that one. These are the only ones that enter. So this already introduces an interesting change. In classical infinite population dynamics, you never compare B with C, but here B with C in small populations is very important. And for n equals 2, it's decisive. If the lights off. And for large population, interestingly, this condition goes to A plus 2B is greater than C plus 2D. And this sort of, it by itself doesn't really look like anything. But then we remember that the unstable equilibrium between this for that and all D in the infinite population case can be written as this here. That's the equilibrium point. And interestingly, that condition is equivalent to the equilibrium point being less than 1/3. And such a law has never been observed in game dynamics. Because there's a famous law by Nobel Prize winning economist Reinhard Selten, x star less than 1/2, which is risk dominance. And I will come to risk dominance and compare this 1/3 law with risk dominance. But here it's 1/3. So this condition for large n, you can invade if the unstable equilibrium is less than 1/3. Therefore, we have a theorem, selection can favor A replacing B for some n. You will be able to find some n where A can replace B. Also because for small w, right? So you can for small w. If either B greater than C or x star less than 1/3. You look at the matrix, you check, is one of these conditions fulfilled? If one of these conditions is fulfilled, you will be able to find the population size such that selection favors A replacing B. And now here's the comparison with risk dominance. So risk dominance means that the equilibrium is on that side of 1/2 or on the other side of 1/2. You ask, what is the larger percent of attraction? Is it A or B? And one way to decide such games is I choose A if it has the larger percent of attraction, or I choose B otherwise. Risk dominance, interestingly, means that for large n, the probability that a single A gets fixed is greater than the probability that a single B gets fixed. So it's the reverse fixation probability. Or here vice versa. So risk dominance determines the ranking of the fixation probabilities of A into B or B into A if n is sufficiently large. Not for small n, but if n is sufficiently large. And then 1/3 determines whether one or the other is actually driven through by selection. So if the equilibrium is here, then selection promotes A replacing B, but opposes B replacing A. If it's here, selection opposes both replacement steps. Here selection maintains the status quo. Selection is against change, and here selection is for change from A to B, but not the other way around. So again, for the emergence of cooperation, if you look at this example, we stick for that and all B, we know that B can never be greater than C. This is the definition almost of all B and dit for that. So you're only left with the other condition, and we have the following answer: selection can favor dit for that invading all B if x star is less than 1/3. So if this unstable equilibrium here is closer than 1/3, then you can find a population size and intensity of selection W such that dit for that replaces all B, starting from a single dit for that player. That's important. And now we can revisit the very famous concept of evolutionary stability by John Maynard Smith, also Nash, in infinite populations. So the definition is that in that game, that's the Payoff Matrix, B is a strict Nash equilibrium if D is greater than B. If D is greater than B, then it's a strict Nash equilibrium. This is of course by Nash, a Nobel Prize winning paper, right? So if B is ESS, that's not John Maynard Smith. B is an evolutionarily stable strategy if D is greater than B, or if D equals B, but then C is greater than A. So again, you see the only comparisons which are ever there are, of course, the comparisons in the row, in each column. And now we can ask, what kind of evolutionary stability concept can we derive from our calculations for finite populations? So very naturally, we say that B is an evolutionarily stable strategy for population size n. If two conditions hold. First, we ask, selection opposes A invading B, and then selection opposes A replacing B. So we have been talking always about replacement so far. This is actually a much simpler condition. You can say, let us look at a population where everybody's playing B, then we introduce a single mutant A. Does this single mutant A have a higher fitness or a lower fitness? It's very easy. It's just a linear condition in N. But we ask that these two conditions hold, and then we would call B an ESS in finite population. So first you have selection against the spread of A, but you also have selection against the completion of A, against the fixation of A. So these two conditions can be written in the following way. B is ESSN if that holds. So that just means that the fitness of a single A player in the P population is less than the fitness of all the P players in that population. And this is our condition that we just talked about before the sign is reversed. That's our condition for B in ESSN. And now for this condition down here, 1 and 2, for small n, again n equals 2 is the smallest, B is ESSN if B is less than C and P is less than C. These two conditions are the same. The conditions go to the same condition, and obviously that's the only thing we need to make sure that B is ESSN. But for large n, B is ESSN if B is less than D, so we discover strict Nash condition, but we also have that X star has to be less than 1/3. Therefore, the traditional ESS concept is neither necessary nor sufficient for small populations, and it's necessary but not sufficient in large populations. And this is where I want to stop.
So we have about 10 minutes for questions.
I have a question on the second part of your talk. I don't know if you have this in mind, but one possible application of practice and spread and the little start to remember how to solve it. Just but the spread depends on the island and the structure is more or less and some small villages around, and then it will go basically from the small village.
Oh, that's interesting. That's interesting.
Apartments.
Yes.
There. And this place, usually the study, but people never know what the leader will start.
Yes. So let me answer the first question first. So we thought about this, and there's one. I mean, we can adapt it. There's one difference, and this is that you have in an epidemic you have uninfected individuals and infected individuals, and normally the infected ones can infect the uninfected ones, but the uninfected they don't uninfect infected ones. So there's a symmetrical difference. But you're right. We can study epidemics on such graphs. Yeah, I know. So we have, Christoph has studied many different graphs and see if they deviate substantially from the Morane process. And I think that for certain scale-free networks, you found amplifying properties. Will you talk about this tomorrow?
Please.
No, so we have not checked with Fisher and Bright, but we have checked with some variations of the Morane process. So in the Morane process, you choose an individual for reproduction proportional to fitness, and then you reproduce it, and you choose something to die. The equivalent, totally the equivalent, is the following scenario: choose two people, and then take the one proportional to fitness. That gives immediately the same stochastic process. And then we have the following: choose two people and compare the payoff difference, and take the one or the other according to a function where it's 1 minus e to the minus, and then the difference divided by something. And this is like then the W interestingly cancels out, as was suggested by one of the referees. But there's a new parameter introduced, and this is a temperature. And the temperature, this is like a simulated annealing equation. And then if the temperature is high, you choose very randomly. If the temperature is low, you always choose the thicker one. So there are a number of stochastic processes where we immediately know the answer. It's very easy. But like for the Wright-Fisher process, it is more complicated because it's not a burst test process, and therefore you have to solve the whole Markov process. But it's clear that we will get a selection for that replacing all in those stochastic processes where the selection gradient is not followed deterministically. That's a robust. But whether or not it's 1/3, I would be surprised if it was 1/3 for all this process.
You had another question?
No, we have not thought about this yet. I mean, you can write down the Mirena process to analyze this. It does go back to these papers by Vickers and John Magnasco. There was a discussion about this that I remember from long ago. So we haven't analyzed it yet. They have not, I think they haven't used. But the Mirena process, then if you talk about, you have to go to 3 strategies. The 2-dimensional stochastic process. So you can have a Mirena process, but the stochastic process is 2-dimensional. That's very hard.
George?
Yes, it seems to me that one of the motivations that you mentioned in the Mirena process is that you can actually solve the forward problem, the analytic sense of this get good estimates. There is perhaps another idea which is go through high dimension situations without necessarily having other graphs or graphs. And there, the direction you can get solutions is by taking large limits and passing through the PDE analog to that.
Yes.
You have it inside.
Yes. So we have used, for example, we've used diffusion approximation for this process. And the diffusion approximation is strange in the following way. At first, because you go immediately to the limit of large n, and then you introduce the diffusion approximation. And so what we wanted to do here is to start a small n. With the diffusion approximation, you do get the 1/3 law, but you didn't get this BC comparison. So the diffusion approximation explained half of the story. I think it's very important now that we know this kind of answer. Let us use diffusion approximation we can compare it with diffusion approximation. We know what we're looking for.
Yes, just one more thing. Perhaps there is a in-between situation where you have a transport process or Boltzmann type equation. And so perhaps you went too far in the
With the diffusion approximation.
and I don't know, perhaps Peter is the right person to talk to. So again, I push my point. Let's talk about ourselves.
Yeah, I would love to see this. I mean, I would like to know if mathematicians can tell me which stochastic process corresponds to which differential equation in the limit of large n. That's what I want to know. Because somehow I thought as a chemist I actually know that. Because if as a student of chemistry I know how to write down a differential equation for the chemical kinetics of any reaction you write down for me. But I also learned in my diploma thesis how to simulate this stochastically. So somehow I thought I know the two sides, but I realized actually I don't, because it's very unclear how they meet. And so, for example, what I described here, the Mirena process, does not converge to the replicator dynamics, at least not, and it very much depends on the order of limits that you take. But if you, for example, think of a Hock-Duff process, where the selection gradient is pointing inwards, then the replicator dynamics has an equilibrium in the middle, but the stochastic process for any n has the weights of the probability distribution on the absorbing states. You have to wait long enough to reach absorption, but this is the equilibrium. And so in that sense, it actually doesn't converge.
Do you have a question?
So yeah, I mean, there's Fisher's fundamental theorem of natural selection, which says that equilibrium fitness is an increasing function of time. And this interestingly holds in a very limited scenario. So this holds for constant selection, but can fail for frequency-dependent selection. But this was very inspiring to physicists, because this is like a first some law of thermodynamics. Yes. But it is limited, so one can immediately write down, so for example, with the prisoner's dilemma matrix, it actually doesn't, because it goes from C to D, and average fitness goes down. And people have looked for quantities that always increase along evolutionary trajectories. And there's the work of Demetrius, and so it has not yet prevailed that field at all.
What I see?
So the applications of that, this describes a large part of theoretical biology, right? So this is ecology and frequency-dependent selection. So I just want to take this and study it in finite populations. Not yet. Yes, I was mentioning, so in the linear process, right? So we have not yet studied frequency-dependent selection in cancer context, but the first part of my talk, we have compared with sort of what people understand about cancer selection. But again, sort of what would be nice and what is not the ended field of cancer genetics is somehow that they give us data where the frequency of mutation versus time or something like this. Doesn't exist.
I think we have time for one more question.
Yes, so first of all, I used branching processes in my first talk when we talked about the probability of escape and so. So the difference here is that you have a fixed population size, and therefore you can't use the branching process if you want to ask the question, what's the probability that the new mutant takes over the whole population? The branching process would be sort of an unlimited ceiling whenever you have that question. And the other thing would be, let us study frequency-dependent selection with sexual mating. So this brings us to a very fascinating sort of field, and this is how to bring together game dynamics, evolutionary game dynamics, which is a phenotypic theory, with population genetics. And this is difficult. It's very difficult. And population geneticists, they like to study sexually reproducing populations with recombinations and this sort of things, whereas we more or less here study haploid populations, asexual reproduction, or it's sexually reproducing, but it's a dominant trait, so we can forget about the difficulty introduced by the Mendelian genetics. Both approaches are valid, so my defense of our approach is that most of the cell divisions that ever occurred on Earth and that are occurring on Earth are asexual haploid. So most of the evolution has happened in asexual haploid. They counter, but what Darwin was observing, what he was talking about was sexual fitness.
So, if there are no more questions, I think we can thank the speaker again. And before we go, there is an announcement.
A few announcements. So I hope the weather is going to permit us to take a picture, and I do hope everybody joins us for the picture. And afterwards, we have the meeting with the students and the foreign visitors. So thank you very much. Oh,
For the reference.
We'll resume at 1.
And I have here, so the second edition of his book is from 1911, which means that the papers are actually from 1904 and the other one is this one from 1916 that I have mentioned is the theory for
committee. Can I have that?
Yeah, yeah, sure.
Okay, so